Alright, welcome to Chapter 9. First video, we're going to be talking about this thing called a significance test. Now, besides significance test, you might also hear it referred to as a hypothesis test, because we are going to be creating hypotheses about certain situations and testing whether our hypothesis meets the statistical cut or not. So today's video is pretty much just a glimpse into what we will be doing for the whole chapter. Now, this whole second semester of AP Stats involves the idea of inference. And inference is we're trying to infer something about our population that we don't know everything about. Now, we just did one thing last chapter in confidence intervals, and we use confidence intervals to estimate a population parameter. And we primarily focused on trying to estimate, oh, that's not a population parameter, we tried to estimate what the population mean, mu, would be based on a sample mean, or we tried to estimate what the population proportion, p, would be. Okay? Now, there are other parameters you could try to estimate with confidence intervals like standard deviations and other things, but we primarily just stick to means and proportions. Now, significance tests or hypothesis tests, we are going to use them to assess evidence for a claim about a population. Now, a lot of the math that we're going to be doing this chapter is still back from that first chapter of the semester. Okay, that chapter 7 stuff on sampling distributions. A lot of it's going to be very similar, especially even compared to last chapter in chapter 8 with confidence intervals. You're going to see a lot of the same type of math. It might just be kind of worked around to look a little bit differently, but you'll notice most of the things. So first, let's see if you can determine when we would use a confidence interval for a problem versus when we would use a hypothesis test or a significance test. So number one, you measure the heights of a random sample of 400 high school sophomore males. The sample mean is 66.2 inches. Suppose that the heights of all high school sophomore males follow a normal distribution with unknown mean, and we're going to say we actually know, we probably really don't know, the population standard deviation is 4.1 inches. You desire to estimate the mean height for all high school sophomore males. Now, we're not testing a claim that we claim to know what the mean height is for all sophomore males. We want to estimate what that height is within a certain range, basically. So this should sound very much like what we did last chapter with confidence intervals. Number two, a researcher wishes to determine if students are able to complete a certain pencil and paper maze more quickly while listening to classical music. Now, in this case, are we trying to estimate the time? No, we're trying to estimate if listening to classical music can be completed, the maze can be completed more quickly than not listening to it. Okay, so this might sound like we could maybe do a confidence interval with this. If we did a matched pairs design, we certainly could. But really, we're going to be testing a claim here. We really wonder, is music better than no music, or classical music better than no music, or maybe a different kind of music? So this is what we're going to be exploring more this chapter with a hypothesis test. And number three, an engineer designs an improved light bulb. The previous design had an average lifetime of 1,200 hours. The mean lifetime of a random sample of 2,000 of the new bulbs is found to be 1,251 hours. So 51 additional hours worth of lifetime. Although the difference is small, he would like to know if the difference is statistically significant. So we are wanting to kind of put this 1,200 number up to the test. Is it in fact the mean average lifetime length really 1,200? Whenever we found from a sample 1,251. Okay, now yes, there is a difference, but is it big enough that 1,251 is a rare occurrence compared to 1,200? That's what we're going to be talking about. And we would make a hypothesis test for this. Now, just like confidence intervals might not capture the population parameter of interest, and we don't know it, remember we said if we did a 95% confidence interval, and we did many of them, approximately 95% would do a good job at capturing the population parameter, and 5% wouldn't capture it. And unless we know what the population parameter is, we don't know if we've got a good confidence interval or not. We just have to hope that we do. So we might make a decision with the significance test, with the hypothesis test that we believe is the right answer, but it ends up being the wrong one. How are we going to know if we made the wrong one? Same scenario applies like we had with confidence intervals. Okay, we may not necessarily know, but we're going to do the math and we're going to try to give it our best go. So here's an example that many of you know very well. Let's make the claim of P equals 0.62, that is the true proportion of all CHS students who do not drink alcohol. Many of you believe that number is an overestimate, that it's overestimated. So you believe, in fact, that that number is a lot lower. You think more people do drink. So let's say we take a simple random sample of 100 students and ask them if they have drunk alcohol in the past 30 days. We find 58% from our survey. So two things could happen. The initial claim, our 62%, is true, but because sampling variability occurs, we're not always going to get 62% in a sample. We just happen to collect a sample proportion that's lower than our claim. Okay, so it's close enough to 62% that we wouldn't question the 58%. Okay, we wouldn't question that it's far enough away from 62% that, I'll take that back, that the 62% is wrong. So it could be just that it's a little bit lower. That's okay. Or our initial claim of 62% is false, so that our 58% that we got was not unlikely to happen, thus proving our belief that in fact our population proportion really should be less than 62%. Maybe 58% is far enough away from 62% that we would really wonder, is 62% really right? So those are two things that could happen. We either have to kind of still go along with our initial claim, versus we can reject it and say, no, it's got to be wrong. Now, our claim that we initially have and the beliefs about our claim, about what we might think might be different about it, we're going to write those in a little bit more mathematical way. And our initial claim that we usually want to try to prove is wrong is called the null hypothesis. And we can abbreviate that as H sub naught. Okay, we might call this H naught. Okay, it's not just H sub 0 or H sub O, it's H naught. So H naught, our null hypothesis, will always use the equal sign. We're going to make a claim that we believe that something about our, that what we feel, something is equal to a certain value. Like we really think that the proportion of CHS students who don't drink is equal to 62%. The belief you want to prove is right is our alternate hypothesis. This is what we want to try to show, to prove things here. And it is abbreviated, or really not abbreviated, excuse me, H sub A. Okay? A for alternate. So H sub A, our alternate hypothesis, will always use one of three inequalities, and the inequalities are greater than, less than, or not equal to. Now we're going to use greater than and less than signs for our alternate hypothesis if we're going to do a one-sided test. And we will talk more in depth about what is a one-sided test versus a two-sided test, which uses a not equal to sign. So we'll dive more into that later on. Now hypotheses always refer to a population, never to a sample. So that means when we write our hypotheses, we're always trying to say that mu is equal to a certain number, or P is equal to a certain number, or any other type of population parameter value is equal to a certain value. Now, not only are we going to have to write out our two hypotheses, we're going to have to define the parameter that we're using, whether it's mu, P, sigma, whatever it may be. Or, as I've got here, you can write what each hypothesis means to the problem, and it's going to take a lot more writing. So you either need to do this much writing or this much writing. And I think most of you would probably prefer this much writing. Okay? But it's up to you. So my null hypothesis is that the true proportion is 62%. Okay? So I can take this and say, well, that's what this really means. The proportion of all CHS students, and I'm saying all here for my population, who do not drink is equal to 62%, 0.62. Alternatively, I think this is what really is happening, that it's less than 62%. So you could write what this really means in words. Or, like I said, you don't have to write both of those things out in sentence. You could just say, well, P equals the true proportion of all CHS students who do not drink alcohol. So basically this statement here is to just say what those two parameters mean there. Okay? So an example we're going to look at. Zach Holland, who's an avid golfer, would like to improve his play because he's a terrible golfer. A friend suggests, I think his friend's name is Nathan, maybe Nathan Notrot, I don't know, something like that. A friend suggests getting new clubs and lets Zach try out his 7-iron. Based on years of experience, Zach has established that the mean distance that balls travel when hit with his old 7-iron is 175 yards with a standard deviation of 15 yards. He is hoping that this new club, this new 7-iron, will make his shots more consistent, meaning less variable, a smaller standard deviation. So he goes to the driving range and hits 50 shots with the new 7-iron. So to describe our parameter of interest, well, typically we're going to be using mu or p, okay, mean or proportion. But here's a case, and this isn't going to happen that often, that we are going to use, we want it to be less variable, so we're going to use sigma as our parameter value here. Okay, and we want sigma to be the standard deviation length of all what? All shots with the new 7-iron. We already know what it is with the old one. It's 15. So we want to try to claim, do we think that it's going to be the same? So here's what my null hypothesis is. We think it's still the same. Nothing's changed. Okay, usually your null hypothesis is the nothing changed factor, if you will. It is what it has been. We kind of have the Eeyore way. It's just the same. Or we can go with the Tigger approach here. That maybe this new 7-iron is better. Okay, his shots are more consistent, which means his standard deviation is going to be smaller than 15 yards. Okay, so really, we're just starting out very basic here. Can you write the hypotheses with the correct parameters and the correct values and the correct signs in between? And what does your parameter mean? Okay, so I want you guys to do this problem. And I want you to come to class the next day, and we will go over this problem together.